All right, so the last part of this section is on doubling time and half-life, okay? So for increasing exponential functions with input measured in time, we refer to the function as exhibiting exponential growth. Now, doubling time is the amount of time it takes for the output of an increasing exponential growth function to double, or basically grow by 100%. Now, for a decreasing exponential function with input measured in time, we refer to the function as exhibiting exponential decay. So you think radiation, that's kind of one of the things with this. And the half-life is the amount of time it takes for the output of a decreasing exponential function to decrease by half or decay by 50%. So what we can do is we can say the doubling time or half-life can be determined by solving to find when the starting value A, so we're going to say an A value, will either be doubled to 2A or halved to 0.5A. Okay, so if we're doing half-life, we'll go to 0.5A. For doubling, we'll go from 1 to 2. Okay. Now, note, 2 points on the exponential curve can actually give us the curve via technology. And so that's going to be one really cool thing. We can plug in those 2 points and do exponential regression, and it gives us the value right away. So that's kind of cool if you ever have that. And so we can show you that maybe. All right, so here we have an example. It says yeast is used in baking bread. It has a rapid doubling time of approximately 90 minutes. All right, now we need to find a model for the size of yeast culture after T hours, given the original size was 2.5 teaspoons. How large will the culture be in 60 minutes? All right, so even though I have technology first, I'm going to do hand first, okay? So what we have is we're going to have some function. I don't know, let's call it, I don't know, f of x, just because I don't want to write anything else, I guess. And we know the original size was 2.5 teaspoons. So that's our A, 2.5. And then we're going to take it times what? Well, we don't know what B is. And it's going to be raised to some x power. So we have a general idea of what we're doing here. But it tells us we're going to double in 90 minutes. Now, we're supposed to be working in T hours. Well, I should probably put this with a T, but I'm using X, but it's going to be after hours. So what is 90 minutes? Well, that's 1.5 hours. Okay, so we have to kind of make sure we're all in the same units. And since B asks for how long it will, or how large will it be in 60 minutes, we have to think about that is 1 hour. Okay, so we can't be switching units around, or we're going to be having a little bit of an issue. All right, so if we're supposed to double, that means the value f of x is going to be now 5, and because we're starting at 2.5, we double that, we go to 5, and then we're going to look for b. Now it doubled in 1.5 hours, so that's our t or x, since I used x. Now what we have to do is we have to solve this. So we're going to divide both sides by 2.5. And so 5 divided by 2.5, well, that's just 2, which is what we would expect. And that's equal to, and b to the 1.5. Now, this kind of gets back to remembering log functions. We're going to have to take the log of both sides. When we do that, we can bring this here down. And so then we have the ln of 2 equals 1.5 ln of b. Divide both sides by 1.5. So the ln of b is equal to, and then we have ln of 2 over the 1.5. Well, we want b, not the ln of b, so that means we're going to have to take this and raise it e to that power, and we'll have to take e to that power. And when we do the e to that power, we get, and this comes down, and we just get b. And so we're going to get b is equal to, now we have to take e to the ln of 2 over 1.5. And so let's go see if I can remember to write this down. Ln of 2 over 1.5. E to the ln of 2 divided by 1.5. And we get the 1.5874, okay? And so that is going to be our B. So 1.587. And so our function is f of x equals 2.5 times 1.587 to the x. Okay, so that's our first part. And I didn't leave a lot of room, but now part B would ask for how large will the culture be in 60 minutes? Well, that's in 1 hour, so f of 1 equals 2.5 times 1.587 to the 1, and multiplying those two out, 2.5 times 1.587 to the 1, we get 3.968 roughly. How many? That's going to be teaspoons because we're going that. So 3.9675 teaspoons. And again, because we start off with 2.5 teaspoons, if we round that, that's really going to be approximately 4.0 teaspoons. And so if we're doing to the 1 decimal place, that would be what it was. You know, you could put 3.968 or 3.97. It all is going to vary, but since I'm going to follow the what they were doing with the 1 decimal place, then that's what I would end up with here. Okay. Now let's do it by technology because it's always good to know this. So what do we need? Well, to do technology, we need 2 points. We need at least the starting point. And at the starting point at t equals 0, we had 2.5 teaspoons, okay? So that was given. Now what does it say? It doubles in 1.5 hours. So at t equal to 1.5, and I guess we could call this hours. This is hours. Then we had what? Well, if we doubled it, we had 5.0 teaspoons. And again, I said we could figure out the exponential with 2 points. We have 2 points, so let's go plug those into our calculator. All right, so stat, edit. Let's clear all this out here. So we had 0, and then we doubled it to the 1.5, so that would be 1.5. And our initial value was 2.5 teaspoons, and then we went to 5 teaspoons. Now we just go to stat, calc, 0 for exponential regression. Now we have to remember, we have to put that back to L2, and then we can go down and calculate it. And we have A 2.5, which is what we found. B is 1.587, which is what we found. And so that's exactly the same thing we got here. So we get f of x equals 2.5 times 1.587 to the x, and that was pretty easy, okay? So sometimes I might say, okay, well, use technology to give me the answer. Sometimes I might say, show me how you got it by hand, depending on the type of problem it is. So you can do it both ways, and it's not too bad, but that's how technology will do it really quick for you. All right, so albuterol is used to calm bronchospasms, and it has a biological half-life. So here we're doing half-lives, not doubling, of 7 hours, and is normally inhaled as a 1.25 milligram dose. So we're supposed to find a model for the amount of albuterol left in the body after initial dose of 1.25 milligrams, and then how much is left in the body after that 24-hour period. Okay, so what do we need to do? Well, we have to think about what the question is asking. We know, and again, we'll do this one first just because. We initial dose is 1.25 milligrams, and then we're going to have B to the X, okay? Now it looks like we're in hours and hours, so I think we're good with leaving everything in hours. We don't have to change to minutes or convert minutes to hours. And so now what we have to do is we have to have a half-life. Now if you remember back here, when we had this, we said, okay, well, we plugged in double and we got the 2.5. And then what did we get after that? We got 2 equals the ln of b to the 1.5, or we really just had the 2 equals b to the 1.5. We can do the same thing here. We can say, well, instead of writing out what is half of 1.25 over here and then doing the division by 1.25, we could actually say, okay, well, we know there's only going to be half as much here when we're done. So that's going to be 0.5 equals b to the x. Now, if we wanted to, we could say, okay, well, 1.25 and go about that and divide that by 2 and get your 0.625 and say 0.625 equals 1.25, divide by 1.25, and we get half. So if you can see how we got to here, that's good. But if you can't, that's what we did. We took 0.625 divided by, or the 1.25 divided by 2 and got that. And so our half-life is here. So again, we need to solve for b. So again, we have to take the ln of both sides. That brings down the x. Oh, and then we already were given x, so I guess we're not having x anymore. It should be a 7, sorry. That's a 7 because that's our half-life. And so when we do that, we have ln of 0.5 equals 7 ln of b. Now we divide by 7. And so now we have ln of 0.5 divided by 7 equals ln of b. Now we have to take e to both of those again like we did last time. And so when we do that, b is going to equal, and now I'm just going to type that on my calculator without having to go back and forth, ln of 0.5 divided by 7, and that's going to be raised to the e to that power. And so when I do that, I get 0.9057. So we get 0.9057, or if we're doing 3 places like we have been, 906. Okay. So that's what b is. And so that gives us f of x equals 1.25 times 0.906 to the x. And so that will be our general form of the equation. Now we want to know how much albuterol is left after 24 hours. So we want to find f of 24. So we take 1.25 times 0.906 to the 24. Okay. So if I raise that to the 24 and then multiply by 1.25, that's going to give me 0.116. So this is going to give you roughly 0.116. And what do we have for units? Milligrams. Okay, so that's how much is left of the albuterol, and then we can albuterol. So that's how many milligrams of albuterol after that 24-hour period. Okay. Now we can also do this technology. T equals to 0 hours. We had how much? 1.25 milligrams. And T equals, now we have 7 hours. We had 0.625 milligrams. So now we have our 2 times and 2 things. And so let's go ahead and plug that in and show you. And so stat enter. So 0. And then we had the, now I forgot what we had, 7 hours. And at this one we had 0 hours. We had, let me look at the problem again, 1.25 milligrams. And here we had the 0.625 milligrams. And now we can do calc number 0. And here's what we had, 1.25 and then 0.906. And that's exactly 1.25, 0.906, what we get here. And so technology, got us there a lot quicker, but, we get the same thing either way. And again, depending on the circumstances, I might make you use technology or I might make you do it by hand. And so being able to know how to do it both ways is very important. Second way, because you need to know your algebra and stuff to solve it. The first way, to know how to do technology to solve it that way. All right, radon. So a building is found to contain radioactive radon gas. 30 hours later, 80% of the initial amount of gas is still present. Write a model for the percentage of the initial amount of radon gas present after T hours. Calculate the half-life of the radon gas. All right. Well, let's think about this. So we're going to have 80% of the initial amount of gas still present. So what we have then, what's their initial value? Well, in this case, what we're looking for is the things more on the right than what's going to be on the left. And so if we say we start with 100%, so 100% is a start, then at the end, we have the 80%, okay? And so what we're going to do is we're going to actually kind of plug everything in what we have and go from there. So we're going to have 80% left. We started with 100%. And then we're looking for B, and how long was it 30 hours later? It's B to the 30, okay? And so this is going to give us what we need to do from the start. And so, before, we kind of was able to plug in some things, and to double it or half it, half of it we divided by 2, and to double it we multiplied by 2. Well, this one, they just tell us there's 80% left over. So we don't have to divide or multiply or anything. We just plug those values in. And because, 80% is left, let's start with 100%, okay? And so now what we're going to do is solve for B. So just about like what we did before. So now we have 0.8 equals B to the 30th. Now we'll take the ln of both sides. That brings down our 30. So ln of 0.8 equals 30 ln of B. Divide by 30. And so now we have ln of 0.8 over 30 equals ln of B. But we want B, so we have to take E to both of those. And so again, I'll just type that on my calculator here. So I'll have E to the ln of 0.8 divided by 30. And that gives us 0.9925. So that gives us B equals 0.9925, and then 8, 9, blah, blah, blah. So B is approximately 0.993 if we leave it at the 3 decimal places. All right. Now, write a model for that after T hours. All right, so that means what we can say is the amount of radon, so maybe R of T is equal to, and now we start with 100, and then we go 0.993 raised to the power of T, and that should give us the amount. Original gas is 100. That's our decay model, basically, for the percent after T hours. Okay, so after T hours, that's going to give us what's left. Now we want to calculate the half-life. Okay, well, half-life, that means when half of this is left. So we want 50 equals 100. And then we have 0.993 to the T. So now we divide by 100. So 1/2, or 0.5, maybe is an easier way to look at it for calculator, is equal to 0.993 to the T. Now we take the ln of both sides. And that T now, guess where it goes? It goes down in front. So now I'm going to go up here because I've run out of space. ln is 0.5 equals T ln is 0.993 divided by ln is 0.993 divided by ln is 0.993. And so T equals, and again, I'll just plug that in my calculator. So ln of 0.5 divided by ln of 0.993. And that gives me 98.67. Let's see, did I do something wrong here? No, okay, just making sure I didn't type anything wrong. 98.674 hours. So that's our half-life, okay? Now, it doesn't say do anything with it. If we have hours, maybe that's the best way to keep it. We could put it to days. We could convert our hours to days if we needed to. But, at this point in time, I think leaving it as that value, that's good enough, okay? Now, technology, what does that give us? All right, so let's look at this one for technology's sake. And so at time equals 0, we had 100. And it's percent, we'll drop the units here. And 30 hours later, so T equals 30, we only had 80%, again, dropping that. And so now we have 0, 100, and 30, 80. Oops. All right, so 0, and then at 30, and then here, oh, I have to enter, and then this one's going to be 100%, and this was our 80%. And again, stat, calc, 0, we have L1, L2, we're good. Oops, there we go. And 100, and then we had the 0.992589, just like what we found right here, okay? And so we get both of them, we get the same thing, which is what we would expect, and just one of them we had to do a little more work to get there. All right, so that would be the things. And again, this is good. Maybe you want to convert it to days to know how many days that is, but you don't have to. And so, you know, that's the only other thing that I could think of that we could do on this problem. All right, last one here I think we have. So investment. Suppose that an investment of $1,000 increases by 8% per year. Write a formula for the value of this investment after T years. Okay, well, what are we going to do? Well, our investment usually is labeled A of T. And so what's our initial value? $1,000. So that's our A. And it increases by 8% per year. So that's going to be, remember, when we do that, we had B minus 1 times 100 is equal to the percent. So this is 8%. So if we divide by 8, that gives us 0.008. And so then we have to basically add 1 to that. So 1.08 is going to give us our value here, and that's going to be raised to the T value. And so that should give us our value formula, okay? So our future value based on the time should be 1,000 times 1.08 raised to the power T. Now, how long will it take for this investment to double? Well, to double means 1,000 is going to be now 2,000. So 2,000 equals 1,000, and then we'll have 1.08 to the T. So we divide by 1,000, divide by 1,000. So 2 equals, then we have 1.08 raised to the power T, ln of both sides. And so now we get ln of 2 equals ln of 1.08. And then we have that times T because that gets to come down front here. Now we divide. And so now T is equal to, and then all we have to do is just take ln of 2 divided by ln of 1.08, and we get the value 9.006. But, you know, that's pretty close to 9, so it kind of depends on how accurate they want it, but that would be years, so approximately 9 years, okay? And that would be the answer they're looking for part B. How long does it take to double? So the easy part was getting our formula, and an even easier part was simplifying and solving for 9. All right, so that's all I have for this section.